Hello, everyone. Um, Today we'll be learning about chemical reactions, solutions, and mixtures. So let's get started. Um, you will be learning about what I just said, chemical reactions, solutions, and mixtures. We'll look in depth at all three topics, understand them, look at definitions, look at example problems, and solving equations and problems with them. So, what is a chemical reaction? Well, a chemical reaction is the process of reorganizing atoms by breaking chemical bonds and forming new ones. Um, so some terminology would be that molecules are a collection of atoms combined by chemical bonds, and atoms are the building blocks of the universe. The atoms are arranged by the chemical bonds. So if we look at this picture down below, we can see these circles, right? And those circles are those atoms, and then those lines in between serve as the chemical bonds. And together, that whole structure is a molecule. Um, you probably have heard of the periodic table of elements. You've probably heard of common configurations such as water being H2O, um, you know, uh, CO CO2, things like that are very common. So this is the periodic table of elements. You've probably seen before, some very common uh, elements such as hydrogen. You've probably heard of oxygen, carbon, copper, nickel, things like that. And in another video, I'm sure someone explains this more in depth. Um, but just to give just to make you familiar with the periodic table, and just to know where these elements are coming from, right? If I said H2O, that subscript for 2 will serve as 2 hydrogen and 1 oxygen. So we can talk about that later. So the basics of chemical reactions: chemical change occurs. The changing of molecules, the reaction either includes atoms, ions, compounds, or molecules. And down below is a picture showing that uh, it involves the change of atoms and molecules, right? You can see from the left to the right the change that something happens, some charge. You see that there's positive and negative there, protons, electrons, some charge is happening to change that configuration. So we'll start. It's very with involving chemical reactions. There's a lot of balancing equations, making sure the left hand side equals the right hand side. Um, and also for each element, you'll see, um, sometimes you'll see their state, their state of matter, either being a liquid, solid, gas, or aqueous solution. Um, this it's important maybe just to understand what they are. They correspond. Their letter corresponds to what state they are, obviously. And you really don't have to use it that often. It's more for complex solutions, but I just wanted you all to get familiar with it just in case there was a problem that we saw it with, that you didn't have to worry about it, and you do not have to worry about it. So the Calvin cycle is when one reaction becomes multi-part. Example, creating glucose, excuse me. And down below, you can see that picture of what I'm talking about. We have an A and B equaling or becoming a C, right? And a C then is dragged down to be used in a different reaction, and then the E's being used in a different reaction. As you can see, how it's multi-part. Why do chemical reactions happen, right? So chemical bonds between atoms are either broken or formed, right? And to the left, there's that picture, bonds breaking require energy. And to the right, we have bonds formation releases energy, right? And we can see in that left-hand picture, right, we can see energy in, and we can see that they're together. These bonds are together already. And to break them requires this energy to split them apart. And you can see now that right-hand picture, the bonds broke, and now they're all separated. However, for when bonds are forming, they actually release that energy out to then build the bonds. So, right, if we want to memorize this, it would be uh breaking bonds takes energy and forming bonds releases energy. Analyzing a reaction. Okay, so it's important to understand the different parts of a reaction, just like you would with any equation or anything like that. And the normal structure will be a reactant on the left. Like there could be one reactant, two, three, however many there will be. It's on the left-hand side. Then on the right-hand side are called the products, the substances on the right. Um, so we have a left and right hand side, and they're separated by an arrow, which points to the direction. But it's key to understanding that the arrow serves as basically an equal sign, that the substances on the left must equal the substances on the right. Okay, and it'll make a little bit more sense when you see the coefficients and subscripts, but it's important to realize that the left must always equal the right. Now, the coefficients are the multiplying number of molecules present. So the coefficient is the number in front of the molecule, right? For instance, let's use that H2O because it's such a common example. If I put a 2 in front of that H2O, well, or no, excuse, let me do a 3 so it doesn't get confusing. If I do 3H2O, what I'm really saying now is that there's 3 of those water molecules. So there's actually now 6 hydrogen and there are 3 oxygen. I distribute that coefficient to each molecule, each element, uh, and when distributing, I do 3 times the hydrogens, but there's 2 hydrogens, so that becomes 2 times 3, which is 6, and then 3 times oxygens, 1. If there's 1 subscript, you don't put it there. Um, and that becomes just 3. Now, the subscripts are the number of atoms for each molecule, right? If we keep going back to, we can do CO2. Well, the subscript there is the 2 for the oxygen, right? Because there's 1 carbon, but there's 2 oxygen present, which is why there's that subscript 2 present. So, right, this is a picture. This is actually a very good picture. It looks like the image got cut off, but to the left is the subscript. To that number in the left-hand corner in red is saying subscript. And you can see this maybe a little bit better. Right, we have a, a formula right? The H2O, we have that's the formula, a coefficient out front, the 6, the subscript, 12. But if we go left to right, we can look at all the subscripts, 6, 12, 6, 2, 2, 2. Same thing for coefficients, 6, 6, and 6. And we can see right left is reactants, right is products, and yields is a great word here. Yields, the reactants yields the products, right? They create the products, right? But they're not creating the products out of nowhere. The left hand must equal that right hand side, right? And there will be more example problems. This is more of a complex problem to balance because, well, you can see that there's a lot of elements that you'll have to do. Balancing these oxygen were probably a little bit on the tricky side. Uh, but yeah, so let's keep going. So the law of conservation of matter, uh, just if we want to get very scientific for a moment, states that atoms are neither created nor destroyed during a chemical reaction. Newton worked heavily with these ideas. He created some laws of motion, but this is one of his statements, saying that a chemical reaction must be balanced. Right, that's the science behind why the reactants yields the products, why that arrow serves as an equal sign, because atoms are neither created nor destroyed. We also can't add these atoms, we can't add these molecules, nor can we take them away. um they're just there, and we can manipulate the equation, right? Just by manipulating the equation, we can have it balanced. And the number of atoms for each element must equal each other on both sides, like I was saying. But there's one of the key things that you should take away from this presentation is that second bullet point is saying that the chemical reaction must be balanced because the left hand side must equal the right hand side. So here is a picture of a chemical reaction. You can see at the bottom, CH4 plus 2O2 yields, or produces CO2 plus 2H2O. And the image just serves as a way to visually see what is going on right now. Now, I told you that that subscript, right? Let's deal with this subscript first, and we can look at CH4. We can look at that 4 subscript. Well, what does that 4 really mean? Well, let's have carbon be that center, right? That the molecule up top, that black molecule serves as that carbon. There's only one carbon, so it only needs that. And then there are 4 hydrogen combined to that carbon. So what that is saying is that there are 4 now gray molecules, attached to create atoms or elements to create it to attach to that carbon to produce that molecule right there, CH4. And there's only 1 in total, so we only need that. We only need that 1 carbon with that 4 hydrogen. And I don't expect you just to understand completely how to create those, where everything should go, but visually seeing that help you to understand what that CH4 means. Now we can look at the 2O2, right? Well, let's just look at the oxygen and the substitute two, oxygen gas. Um, that's just saying 2 oxygen combined, right? And that's why there's 2 reds combined, but there's two separate ones, right? Because of that 2 coefficient in front, saying that there has to be two of those two, right? So in that one, we both have a coefficient and a subscript that we have to worry about. Now we can look at that CO2, carbon dioxide, um, which is just that carbon in the middle again and the two oxygen out on the left. And remember, there's no subscript, I mean, there's no coefficient there, so we only need that whole molecule there. And finally, we have uh, two water molecules, two H2O. You can see the oxygens out in the middle, that red molecule, and two water to the right and left of that molecule. But we have two of those water molecules, right, because of that two coefficient out in front. I hope that made sense. You can also pause the video just to, take another look at it to maybe just visually picture it longer. So we can go into chemical reaction types, right? There's a called irreversible and reversible. The irreversible states that chemical reactions uh, go only one way, while reversible say that they can either go backwards or forwards. And there's also another term right there called equilibrium. The chemical becomes balanced by both the reactants and molecules, and reactants and products molecules, excuse me. The five types of chemical reactions are the synthesis reaction, aka combination reaction. We have decomposition reaction, single replacement reaction, double replacement reaction, and combustion. And there's a little asterisk at the five because these are the majority five reactions for the most part. There will be a little bit more complex ones, but these are the five that are you will see most common and we have to most worry about. So what is a synthesis reaction? A synthesis reaction is when two or more substances combine to create one new substance. Right, we can look at that general form. Now, what's that general form mean? This is saying that this is the basic function, the basic component of each of these reactions. We'll have an A plus a B forming, yielding an AB, right? That they combine together, right? Think of synthesis, combination, the synthesis meaning creating something, forming something together, adding two things to make one, is what we do for synthesis reactions. We have Na, and in this parentheses, right? We have those states of matter I was showing you about. Don't have to worry about it right now. Sodium chloride, and magnesium, oxygen gas forming magnesium oxide. Right, the Na and Cl2 they combine to make NaCl. Mg and O2 combined to make MgO. See, that A is the Na, the A is the Mg, the B is the Cl2, the B is the O2, and that becomes NaCl, MgO. They become one, is what that synthesis is saying. And there are those coefficients out front to balance the equation, right? We need the same amount of Na on both sides. We need the same amount of Cl2 on both sides. And just if you're just to understand why there's no subscripts on the right hand side for the NaCl or the MgO is because the Na and Mg both have a charge of 2. So when the charges of 2 and the chloride and oxygen gas combined, they actually cancel out to form just NaCO and MgO. So from there, we just we need to balance the all the um, elements. So this is another example of a synthesis reaction, and you can see it a little bit more visually, is why I include this picture. I think it's important to see this visually to picture it right. We have Mg, but we have that coefficient out in front, right? So there, that 3 in the coefficient says that there's 3 Mg. So each of the purples serves as an Mg. Now we have N2 with 2 and 2 combined, right? It's one whole thing, but there's 2 of them. We combine them, there's 3 Mg combined with the 2N, the nitrogen gas, and they combine to form Mg3N2, right? And you can see that there's those 3 purples and those 2 Ns all combined to form one structure. The decomposition reactions. Now, the decomposition reaction is actually the opposite of synthesis, right? I see at the bottom, see how this compares to the synthesis. The answer is that it's the opposite. The compound breaks down into 2 or more other substances, right? Instead of forming decomposition, right? The little word decomposition means, breaking down, you know, the destroying, the not destroying is a bad word, but breaking, splitting, separating. And we can see that general form being AB yielding A plus B, right? The opposite, right? We for synthesis we had A plus B yielding AB, but now we have AB yielding A plus B. And what does that look like? Let's see some examples at the bottom. All right, we have HGO yielding Hg plus O. That 2 after the oxygen should be a subscript. I do apologize for that. And we can look at CaCO3 and CaOCO2. You can see the separating. The second one's a little more complex, but you can definitely see from the HGO into the into the Hg and the O. All right, and this is a good picture. I like these. I like visually showing you these pictures. You can see the decomposition, the NaCl, Cl, and Na yielding Cl plus Na. Right, the A is the Cl, B is the Na, forming ACl, B, Na. Now we can look at the single replacement reactions, where one element replaces a similar element in a compound. Now this general formula is a little more complex, right? Because we now have A plus BC yields AC plus BC. All that is happening really here is the A and the B switch spots. The A goes to the AC and the B separates to B, right? It's important to understand that the A represents a metal replacing B another metal, right? So those are both metals. Now the same thing is down there, y plus xz yields xy plus z, except y is a non-metal replacing z another non-metal. So that is important to understand. Right, and let's look at single replacement continued. Some figures down below, some examples I'd given. You can also see, right, those arrows showing, the Mg takes the spot of the Al, and that means now the Al aluminum becomes by itself, and the magnesium goes to the chloride. So now that's why it's important to understand the periodic table of elements to understand what are metals, what are non-metals, and so forth. The Br takes the K spot, um, Ki. Yeah, and that forms I2 plus K. The examples above show a little bit more complex. If you want just to take a look at those as well, but I do think the pictures down below are good. Now we have double replacement reactions. These are positive and negative ions of two ionic compounds, switch to create two new compounds, right? Now this is a little bit more complex. We have an AB plus CD yielding AD plus CB. So the A and the C are switching spots, right? It's basically what's happening. The A and C are positive and B and D are negative. Double reactions continued. I gave an example of a double reaction up top, but also at the bottom you can see a little bit better, right? It even shows you how many there are in each for when balancing it. We have an Na will take the spot of the sodium will take the spot of hydrogen, and hydrogen will take the spot of sodium, forming those two new compounds. You can see how those two just switch, and it even shows you at the bottom how to balance it. Right, with the two hydrogen needs to be on both sides. Two sodium needs to be on both sides as well. We have lastly the combustion, which contains oxygen gas releasing energy and light and heat. Right. The general formula for this is fuel plus O2 plus CO2 plus H2O. An example at the bottom, we have hydrogen, right, is being the fuel, the 2H2 hydrogen gas, and the rest is the same, right? This is a little more of a picture, more of a visual picture that you can look at. We have, CH4 being the fuel, and this is the picture I showed earlier to you actually, but waited to tell you that this is a combustion reaction. So let's look at ionic and molecular compounds. Just as a little joke here on the right hand side, I have what is the chemical formula for banana, BaNa2. Just a little joke, right? Right, because the Na would serve as 2. So what are ionic compounds? Ionic compounds are a charged molecule or atom. They can either be neutral, negative, or positive. An anion is an ion with a negative charge. Cation is an ion with a positive charge. Down below is the structure of an atom. You've probably seen it here and there before in the ionic compound. The basics of naming ionic compounds. You When you do take chemistry, you will get a little bit more in depth in this concept. But for now, just the basics is understanding, the compounds named by the first, uh, but which is the cation, the metal goes first, then by the anion, the non-metal. The cation does not change its name. However, the anion does change by removing "ide" and replacing it with "ide." "Ein," excuse me, that should be "ein," replacing it with "ide." I apologize. For instance, NF is called sodium fluoride. Right? Examples of naming some compounds with copper chloride, um, becoming uh, many different ways depending on how what charge the copper has. Um, right, we can see that it could be copper chloride, or copper chloride 2. It's important to have those Roman numerals there as well, right? And what are some Roman numerals? Are It's important just to understand what they are for the charges. Um, Really, the most important are the first 5 here. One line is separate, means 1. 2 lines means 2. 3 lines mean 3. A line and a V then mean 4, because if a number after a smaller number, if a greater number goes after a smaller number, you subtract the two. So it's a V is symbolizing 5, and 1 symbolizes the dash symbolizes 1. So it's 5 minus 1 equaling 4, and then we have the V for the 5. Oh, and there was a video on the other side if you'd like to see it. So some examples of ionic compounds down below is just naming it, right? There's sodium, calcium, potassium, aluminum. Those do not change their names. However, the others add the I to it, right? Fluoride, sulfide, oxide, phosphide, oxide again down below with magnesium, right? The metal in red, the non-metal in blue. It's very important to understand that the metal does not change its name, and the non-metal becomes ide. So molecular compounds are made of at least 2 elements that share electrons, a negative charge that combines the element by a covalent bond. And to the right are those covalent bonds. You can see them getting combined together to form a molecular compound. Naming molecular compounds are a little bit more tricky. Remove ending and add the "ide." Use prefixes, exception if the first element has only one, then no prefix is needed. Combining vowels, example. Monooxide becomes monoxide, right? We combine those 2 O's together to form monoxide. Just it's simplifying it. These are the prefixes, the 10 prefixes: mono, di, tri, tetra, pentra, hetra, hexa, hepta, oxa, octa, nona, deca. And I gave examples there. You'll learn more and more that the for prefixes, you'll get more comfortable with it, because you'll start using it for shapes, right? Looking at polygons, in geometry, things like that. When you do use these prefixes without even realizing them, will help you in this. Just examples of molecular compounds are down below. You can just see the examples if you want just to pause the video and just take a look at them. So balancing the chemical reactions, like I said, think of it as an equation. The left must equal the right, and that's it. So let's get into it, right? Steps of balancing chemical reactions. Step 1 is take inventory of the elements and atoms of the product and reactant side. Step 2 is it balanced. Step 3, if unbalanced, change coefficients until it's balanced. And that's it, right? Those are 3 pretty simple steps. We have the CH4 plus the 4Cl2 yields CCl4 plus 4 HCl. And what we did there was we started with 1C, 4H, Cl was at 2, but by adding that 4 in front, we made that an 8. And we had 1C, right? And the H becomes a 4, right? If we add a 4 out front, and then the Cl becomes an 8 with that 4 out front. So let's look at a practice problem. We have 3C, 8H, 2O, 3C, 2 is for H, and 7 for O, right? But we need to balance it. By balancing this equation, all we have to do is add a 4 to the H2O to make the water 8 and the oxygen 10. Now the trick here would be, because carbon is already balanced, let's not worry about the carbon, because it already gives you that 3 out in front. And for the 4, we can just, by adding that 4, it makes the hydrogen equal, right off the bat. And you can then see that the oxygen becomes equal as well, right? Examples. Let's do this one together, right? We have, I showed you at the bottom, right? We have 2H initially and 2 oxygen. On the right, we have 2 hydrogen and 1 oxygen. To make it equal, we need to balance the oxygens, because the oxygens do not equal each other. To balance the oxygens, we need to add a 2 coefficient in front of the water. But however, that means that the hydrogen now becomes 4 and the oxygen becomes 2. And because that happens, we then need to go to the left, because now the oxygens are balanced, but the hydrogens are not. So we need a 2 coefficient in front of the hydrogen gas to balance it. So you can see the answer at the bottom. 2 hydrogen gases with now 2 water molecules are now needed. So let's do another one, right? S corresponds to 8, O corresponds to 2, S corresponds to 1 on the right, and oxygen corresponds to 3 on the right as well, right? Well, how do we balance this, right? We should start with the sulfur, right? We should balance that. And to balance that, we need an 8 out front to make it 8 equaling 8, right? So we have the 8 out in front of the sulfur, oxygen 3. And that, but the oxygen is now 8 times 3, so that becomes 24. And because we need to balance it on the right as well, we need to put a 12 out front of the oxygens to make it now 24 oxygens on the left-hand side to balance it. And you can see that answer at the bottom. So let's try another one. We have, oh, that is the same. My apologies. So let's try one on your own. Pause the video now if you'd like to see it, and try it on your own. The answer, right? The answer is that we just need 2 hydrogen chloride on the left, right? We only need that 2. That way we can balance the hydrogens and the chloride at the same time, and we don't need to change anything about the zinc, right? Let's try another one on your own. This is a little bit more tricky, right? At first, the sodiums are the same, the Na are the same, and the the oxygens are the same. However, the hydrogens are 3 on the right and 2 on the left. So we need to change that. By changing the hydrogens, we need to make the hydrogens on the right even. So we add a 2 to the NaOH. However, that makes now sodium and oxygen 2. And then hydrogen becomes 4. So then to balance that back on the left-hand side, we need a 2 for the Na, so the Nas are both 2. And then 2 out front for the H2O. That way we have 4 water molecules on each side and then 2 oxygen molecules on each side. Another one on your own. Right, this one is a little bit more tricky, right? This is a combustion reaction. And the reason why it's tricky is because numbers do get a little bit higher, but it is important, right? We can start right. Well, let's just pick a element. Let's say we pick hydrogen, right? Let's pick hydrogen. We see that there's 12 on the left-hand side. So there must be 12 on the right-hand side. That's why we can just initially put 6 oxygens on the right-hand side. Okay. Right, because that 6 times 2 is 12. Now, we'll come back to what that does to the oxygen in 1 second, because we also see that carbon has a 5 on the left. So that means carbon must have a 5 on the right-hand side also. So we need a 5 in front of the carbon. So the 5 in front of the carbon balances the carbon and hydrogen. Now we need to look at the oxygen. The oxygen on the right-hand side has become 5 times 2, which is 10, and 6 times 1, which is just 6. So 16. So that means we just need an 8 in front of the oxygen. And looking at it that way becomes much, much simpler. This is an interactive balancing simulation. If you click on the link, it's a really fun game. It's the website's called FET, and it's just balancing chemical equations. Right, you just all you have to do is just drag the number and it'll balance it uh more and more so let's look at solutions now. A solution is a homogeneous mixture composed of at least 2 substances. Now we'll go back to what homogeneous means in a second. The 2 components of a solution is a solvent and solute. Solvent plus solute equals solution, right? That picture at the below serves very as the simple justification. And an easy way of remembering what a solvent is, being that liquid, is water is called a universal solvent, right? Water is a universal solvent, and that makes it very easy to understand what the solvent and solute difference is. So solute is a substance that makes up the smaller portion of the solution, right? This is a substance that is dissolved, right? If we have an example, salt water, the salt is a solute and the water would be the solvent, right? And that's the picture about down below. The solute being that the sodium and the solvent being uh the water, right? And we have a solvent, right? Is the substance that makes up obviously the greater portion now of the solution. This is where the solute is dissolved. To the right, we can also see a picture of that solute and solvent in the water, right? That looks like it could be, maybe salt water, let's say, and that solute is that those yellow is that salt, and the water is obviously everything around it. Solubility is a term that means the amount of a solute that can be dissolved by the solvent. Right, we can see, a soluble substance and insoluble substance, right? You can see the pile at the bottom. Examples of solutions, right, that you probably see every day, right? Juices, carbonated drinks, salt water, coffee, or tea. Types of solutions, we have a solid solution, liquid solutions, and gas solutions. It's not, you don't have to exactly memorize it, just understanding that there are these different types of solutions, and the different forms that they can come in. This table does show some examples. uh, here's a chart, right, of solid solutions. Just knowing, what the solution does produce, and some examples, right? We have liquid solutions and some examples down below as well, seltzer water, alcoholic drinks, tea, salt water, things like that. And gas solutions, air and natural gas. Saturated solutions, where the solute cannot dissolve anymore, leaving the undissolved substances at the bottom. And at the bottom shows saturated solutions, right? Uh, but you can see in figure 1.3 that there's still solute at the bottom. Unsaturated solutions, you can obviously see, would be the opposite, where the solution can completely dissolve the substance, leaving nothing at the bottom. And you can see now in figure 2.3 that there is nothing at the bottom. And pure substances, these are the opposite of mixtures. They make up of only one kind of particle, that should be particle, and have a constant structure. To the right are examples of pure substances, chemical elements, compounds, crystals, elements and compounds. Elements are substances where the atoms are the same as the protons, and a compound are substances that have at least two chemical elements, or should be elements, my bad, bonded together. Um, this is just a picture, just to maybe, this is actually a very good picture just to see it, right? We have matter at the top, right? Everything is matter, either a solid, liquid, or gas. And those go into two different categories: mixtures or pure substances. Pure substance, right, is in its name, constant composition. Mixtures, variable compositions. You've probably heard of both, right? A mixture, check mix, or trail mix, whatever, just various components. Um, and mixtures then become into heterogeneous mixtures and homogeneous mixtures, and elements and compounds for pure substances. Differences between pure substances and mixtures. Pure substances cannot be broken or separated. They're constant physical and chemical properties, and there is only one substance, while a mixture is, they can be separated. They do have different physical and chemical properties, and there are at least two substances. You've probably heard of this word electrolytes, and electrolyte is an ionic substance that are soluble in water due to hydration, minerals that have electric charges, right? And these are all examples. You probably drink, a Gatorade or a Powerade, or something like that, some energy drink, and you are getting those electrolytes from those drinks, to you have them during sport games and things like that, just to give you that extra boost. Just a little extra, right, is a pH scale, which measures the amount of hydrogen ions that exist in a solution. And it's separated by 0 to 6.9 is called acidic, and 7.1 to 14 is called alkaline. And those are the different types of where it would be on the pH scale, and 7 is considered to be neutral. Buffer solutions that can resist changes in pH establish stable hydrogen ions in the environment. We have acids, right? These are the high concentrations of hydrogen ions. Excuse me, these are high concentrations of hydrogen ions, which create the low pH, right? And those examples of acids, right? Most commonly, orange juice, lime juice, lemon juice, vinegar, aspirin, yogurt, Coca-Cola, all types of acids, right? But we have bases, which are low concentrations of hydrogen ions that create high pH, right? And those are examples at the bottom, right? Some baking soda, some cleaners, things like that. Tums, right? And like I had said earlier, neutral. So pure water is neutral. pH of 7, and it's considered neither an acid nor a base. It's directly in the middle of the pH scale. Finally, mixtures. A mixture is composed of at least two or more different. Oh, excuse me. A mixture is composed of at least two or more different substances that have physical properties. Right. The two mixtures are homogeneous and heterogeneous, where there are at least two different substances that aren't combined chemically, right? We have that salt water is homogeneous, and oil and water is heterogeneous because they actually don't combine when you mix them together. They will stay separated. You can try that at home. You can have a cup of water and put some oil in there, and you can see that the oil won't really interact with the water. However, if you put salt in water to make salt water, you won't even be able to see the salt once you stir it around. Right, in these heterogeneous mixtures, two or more chemical substances with the different parts cannot be distinguished. Now, I put that down there because you can see that's how I sort of think of a heterogeneous mixture, is when all the components are different and then combined. Um, and homogeneous mixtures are when two or more chemical substances where the parts can be distinguished. And this is, an example of blood. At the bottom, those are blood where they cannot be distinguished. Homogeneous versus heterogeneous mixtures. This is a picture basically where you can tell the heterogeneous won't interact. Uh, you can see the separation of the red and the green. However, the homogeneous mixture will interact, and you can see how they're all combined. Just some things to know about mixtures is that in compounds, the substances chemically combine, forming molecules like H2O. When creating a mixture, no new substances are formed. And you can see a mixture down below is, they are separated like this heterogeneous and compound. It's the H2O molecules. Example is tap water, right? This is a mixture. Tap water has all these different minerals in it to make it a mixture, and then we have distilled, obviously does not have minerals. And just also colloidal mixtures is a homogeneous combination of a solid or liquid particles combined by a liquid um, or gas solvent. I apologize for the spelling, and there's a picture at the bottom. Suspension mixture is also our mixtures that are stirred together by two or more ingredients. Particles are normally able to be seen by a magnifying glass. There's different ways to separate the mixtures: distillation, filtration, evaporation, and chromatography. Distillation is a way to separate a liquid from a mixture that's composed of more than one mixture. The next slide will show that liquid ethanol being separated from a mixture, right? And there are different steps of the distillation, right? We can see step one being water and ethanol solution, and then we have an electric heater that heats up that water and ethanol solutions. Right, and that pure ethanol, but now becomes a vapor, and the cooling water separates. The vapor condenses in the condenser, um, and by cooling that water, now we have ethanol separated from the water. And then that step three, right? We can then see even more so. uh, fil- filtration. Example would be sand in a glass of water. Right? How would we filter that to separate the mixture? You would filter the water from the sand, aided by gravity. In a mixture of salt and iron, right? The iron can be removed with a magnet. Just different ways of filtering it out, right? You can think of it, like if you're cooking and you need to filter the water out, you have like those poked holes and you filter it out. It's the same concept. Um, Evaporation is a way to separate homogeneous mixtures when salts are dissolved. This usually involves heating the mixture. And below is, evaporation, right? A Bunsen burner is a way just to heat up uh, some water, right? And that can evaporate it. Chromatography is a way of separating a mixture by putting in a solution by a medium where it can differentiate it, especially using colored pigments. And you can see down below there's different colored pigments. A little bit about myself is my name is Aiden Silverman, and I live in Baltimore, Maryland. I'm a junior at Boys Latin. I love to play sports, especially soccer and lacrosse. Thank you for listening to my video. And these are some of the sites I use. Please, if you want to look, take an extra look. There are some great sites just to get some extra practice. Thank you.